Hi, everyone. Usually I say thank you for coming, but you didn't have a choice because there's one track, which is great. But I do want to thank the PyBeach organizers for all the hard work they put into this. It's really fun to present to the local Southern California community here. So today we are going to talk about static typing in Python, and hopefully I'm going to illustrate to you what I think is a really interesting paradox. And along the way, we're going to learn some things about Python from the bottom to the top. So we want to talk a little bit about what type hints can and cannot do. In code that I see in some of my colleagues and others, I think there tends to be some confusion about this. We really want to expose the distance between static types and runtime reality, and that distance might be greater than you think. And finally, hopefully you'll come to get a sense, an understanding of what I really see as a paradox. So what is this paradox? I formulate it like this. Python implements dynamic type behavior using a statically typed language, C, only to then offer static type annotations on top of a dynamically typed language, Python. Okay, we'll come back to that. A little bit about me. I think this was all covered previously, so I will go through this very quickly. I will mention that in my work on implementing static frame, that's what really led me to dive into Python typing and statically type that entire library, and also find some new and novel ways to statically type data frames, which I think is a really interesting problem. But along that time, I spent many hours statically typing my Python code, which brought no real benefits to my users, no benefits to my performance, and left me thinking very often, is this worth it? And that's kind of what motivates some of these questions. I think it is, but we'll come back to that. Okay, so first we're going to dive into runtime and statically typed Python. Python is a dynamic language. Everything is a PyObject subtype. So everything is a subtype of a PyObject, and we'll see what a PyObject is specifically later. Any subtype can be assigned to any name. That's really what makes it dynamic. And as a consequence of that, type discovery is necessary. So let's look at a little bit of type discovery. Here we have a function. This is a lambda function that is going to randomly choose one of 4 types. If we call this function, we've assigned this name A, we have no idea what this type is. We do not know. And Python gives us a number of ways to discover the type or the behaviors available with this instance. We can call isInstance, and that can tell us, well, it's not an integer or an integer subclass. Okay, that's fine. We can see if the type conforms to a behavior, to a protocol, and this is commonly known as duck typing. We can see in this example, is A iterable? If it is, we're going to get back a type of iterator, and we see here we get a clue, it's a dict key iterator. So now we kind of know. If we call type, we will see that this is a dictionary. So dynamic languages have many benefits. They provide ease of use and are easy to learn. These are not trivial benefits. Ease of use and easy to learn means that we can rapidly prototype code, we can work quickly and efficiently, and extremely important, we can bring people into the language. People can use Python without committing much time to computer science, and that has been extremely important for the development of Python. Furthermore, with dynamic languages, we often can skip a lot of boilerplate. Our code is more concise. That makes it easier to read and easier to maintain, and that is a very important thing. Now, there are some detriments to dynamic languages. This type discovery that I've already shown is expensive, and we have to do it in Python both at the C level and at the Python level, which I will show you in a little bit. We also don't get strict interfaces. A function can't say, I only take integers. We can pass a Python function anything we want, and that means we have to deal with more complex behaviors. Furthermore, dynamic languages like Python prohibit us from really doing comprehensive static analysis. We can do some static analysis, but we can't completely understand what the program is going to do until we run it. So how do we mitigate some of these detriments? Well, we can add static types on top of our language and improve it. This gives us strict interfaces. That's one of the things that we want. With static types, we can now say this function only takes integers. And we can perform fairly complete static analysis, depending on how complete our static types are. And that lets us analyze our code, find errors, find bugs, before actually running the code. But for dynamic languages like Python, this requires us to operate on another layer. And that transition to another layer is really what leads us into this somewhat paradoxical situation. So Python's progress towards static typing has been an incremental and a long journey, and a journey that's probably not complete yet. Function annotations was the foundation of what made static typing possible in Python, and that came way back in 2006 with PEP 3107. It was a number of years later, in 2014, that it was sort of formally decided, okay, we can use these annotations for typing, and here's how we're going to do it. This is almost over 10 years ago now that it was asserted that, okay, we're going to use annotations for typing. And there's a couple key approaches in those early assertions of how to use typing in Python. First, we're going to use Python syntax and PyObject. And that's kind of interesting because it actually didn't have to be that way, but that was a choice. We're going to embrace gradual typing. Gradual typing is not a casual term, but a technical term for being able to gradually add type components to a system without obligating the user to have typing everywhere. That's what would happen if you were to use a pure static typed language. You would have to have types everywhere. With gradual typing, we can incrementally add types, and that is very important. Furthermore, it's very important within Python for the static typing to minimize or have zero runtime influence. And we'll see how that further separates the layers of static typing from runtime Python. Okay, so let's look at some annotations. In the beginning, as I mentioned, annotations were designed for runtime usage. And while they were conceived as useful for typing, they could be used for other things. And in fact, any Python expression can be an annotation, and a lot of people may not know this. So for example, in this funny function here, we see that the parameter x has as its annotation a complete function. We can pack a function into our annotation, and the return annotation is not a type, but maybe a docstring. Now, no matter what the annotations are, we can look at the dunder annotations attribute and get those attributes out, get those annotations out. And we see here that we have a function and a string. Those are weird. Most people don't do this, but the annotations permit it. Now, by 2017, after people had been using this for a while, typing usage of annotations sort of dominates how annotations are used. And we start to realize there's a problem here because these annotations are built in Python. They're Python objects, and creating Python objects and evaluating Python expressions causes runtime overhead. So a feature was added in 2017, PEP 563, to say from dunder future import annotations, to defer annotations, to keep them as strings and lazily evaluate them only when needed. And we can see this right now in Python 3.13. If I create a variable x and I annotate it as 1 divided by 0, this is going to immediately give me a 0 division error. We're going to evaluate the annotation eagerly. If I just import from future import annotations, then that waiting exception is silenced until I go and look at that annotation later on and it gets evaluated. So there are trade-offs to this deferral of annotations. We avoid the costs of annotation objects, which is great. That's really good. But it hides flaws. It hides incorrect type annotations or invalid Python or expressions that are going to raise errors. And it really further separates these two layers, the runtime layer from the static typing layer. And this is going to become the default in Python 3.14, which I think is good. We will no longer need to import annotations from the future, but these consequences of the gap between these two layers still remain. Okay, so most people use annotations for type hints with something like this, a function that takes an integer, a float, and a boolean, and then returns another float. But as many of you know, the runtime completely ignores those annotations. So I could have this function, and if I want, I can call it with a string instead of an integer instead of a float, and then a truthy tuple instead of a boolean. And what I thought I was going to get a float, but now I get foo, foo, foo. Okay, so the runtime completely ignores the annotations. That's okay. Now, we need more than just annotations to completely type our code. And so in the typing module, we have bunches and bunches of other things that help us statically type our code. And in fact, expand the static typing meta language, if you will, into something well beyond runtime Python. These exist in the runtime, but they kind of evaporate. And I'll show you what I mean by that. We'll look at two examples, the final decorator and the overload decorator. So The final decorator allows us to decorate a class and say, this class cannot be subclassed. You cannot create a subclass of this class if I annotate it with @final. Well, in the runtime, you can subclass it just fine. The runtime doesn't care. It's just an annotation for the typing system. We do leave a discoverable remnant on the class. We can look at dunder final and see, but it's not enforced at runtime. Another example is the @overload decorator. Many languages have overloaded functions where different function signatures can be called and picked up based on the arguments given to a function. Python does not support overloads. Overloads are not permitted in Python, and yet our typing system lets us do overloads because it's quite a convenient way to express typing relationships. Here we take in a string and return an integer. Here we take in a sequence of string and return a sequence of integers. And finally, we define the real function. This is the only function that remains. We've stomped over those previous names, and only one count exists. Python does not have overloads, but we are telling the typing system that these are some typing patterns that might emerge from this interface. Now, just like as we saw with final, we can get back to that information. We can use in the typing module a getOverloads utility function that, given the function, will actually get back those overloads, which is kind of cool. We leave a trace of them, but the runtime ignores them. So again, Python's static typing is almost like a parallel meta-language that sits on top of the runtime language. It is deferred or ignored entirely in runtime and implements things that actually cannot be done in runtime. And kind of interestingly, kind of strangely, it's built with dynamic Python objects and syntax. Okay, now we're going to go in a completely different direction. We're going to go from the bottom up, and we're going to look at what this is all sitting on top of. So CPython, the most common implementation of C, the one you probably all use, is implemented in C. And this was a good choice in the 1990s when it was first implemented because it's fast and it's flexible in just the right kind of way. Now, most people might not think C is flexible, but we'll see. So C is statically typed. It gives us strict interfaces. It can be statically analyzed. We like that. It does require manual memory management, which is tricky and hard and error-prone. And it gives us an extraordinary freedom to cast anything to anything. And that comes with some challenges. With that casting, we are able to do polymorphism with structs. And that is a key feature which I'm going to be pointing out today. So first, we need to understand a little bit about how casting works in C. So the memory of a value or a struct can be reinterpreted. And this is very powerful, but crazy, and a source of terrible bugs. But anyways, so here I have an integer that's 65. This is a very simple case. And I can cast it to a char just with those little parentheses there. And I can say, hey, compiler, you used to think this was an integer, but now it's a char, and just treat it like a char. And I can print it out, and I get the ASCII corresponding character, A. Okay, that's all well and good. But we can do more dramatic things. So for example, I can interpret the memory of a struct. Here I have a struct A that has one 32-bit integer, x. And then I have another struct B that has two 16-bit integers, y and z. I can create an instance, if you will, of that struct A, and then I can tell the compiler, hey, don't think like of A as A anymore. Think of A as B. And I can cast it to a pointer to B. And then I can read the field Y, and I get half of the original A. And I can read the field Z, and I get the other half. We've reinterpreted the memory, and we can just pop it right off and get it back, which is pretty wild. So this ends up being a key feature in C, which permits the polymorphism that makes dynamic Python possible. Dynamic behaviors flourish with polymorphism. It might be not too strong to say that is what is required for dynamic languages. We can handle different types with common interfaces, and that gives us a lot of reuse. We can implement polymorphism with protocols, interfaces, or subclasses. We can do all those things in Python and other languages, but we can also do it by creatively casting our structs. So how do we do polymorphism in C? Well, C is a fairly old language by now. It was released in 1972. And not initially, but later on, a feature was codified as the struct first member rule. And this was codified in ANSI C with the statement that a pointer to a structure object, suitably converted, that means casted, points to its initial member. This is the only guarantee. You can do crazy casting in C that's not permitted, that is undefined behavior, but this is guaranteed. This is defined behavior. and this permits our polymorphic structs. So we're going to dive further into this, and I know this is some C code, but hang on, and I think you'll get to see where we're going. So here I've created a struct called message prefix. Imagine we're going to create a logging system in C, and we want to have a struct that we want to be able to log various different types of message. But we know every message needs a priority and a timestamp. So we've defined a struct here that has two fields, priority and timestamp. Then we're going to have specialized versions of this message for different purposes. Maybe we want to log long text messages, but we still want priority and timestamp. For that, we can create a new struct, message text, that has prefix as the first member. This is a kind of derived class in our object-oriented language. And then we can add an additional field for the text. We can define another struct. This one is message status. This also has message prefix as the first member, but then two additional fields for job ID or progress or anything else. Again, you kind of might think of this as kind of a subclass of the original message prefix. It doesn't look like your normal subclasses, but we get some similar behaviors. And one of them is reuse. So for example, here I have a function called printHeader. This takes a message prefix and reads from its fields. This interface will only work with message prefixes. Now I have a function for printing a message text, but I want to get that common stuff out of this struct. So fortunately, C lets me just cast that message text pointer into its first element, into message prefix. And then I can reuse this common function. This is kind of like calling into a base class. And then I can do my specialized behavior with what's left. And we can do the same thing for message status. We can leverage that the first component of the pointer is the message prefix. We can cast it to it, get the reuse from a common method, and then go on and do our specialized operations with our, if you will, derived struct. Okay, so the reason I'm showing you all this is because this is exactly how Python works. This is the key thing to how Python works in C. And this is because of the PyObject. The PyObject is a struct that essentially looks like this. This is the core to all the Python code you've ever written. Now, it's much more complicated now because of free threading, which is great, but this gets much more complicated. But this is essentially what it is. We have a struct that has obref_count, which is for your reference count, and we have a pointer to the type. That is it. Every Python object has this struct in it. And yet we can create a whole range of alternative and more complicated and interesting Python objects. Now in the CPython code, we can get a lot, we can sort of enforce that every PyObject, derived PyObject has this functionality by using a macro to encode that every struct should have this OB_base field. And so we see here, this is the actual Python struct from the CPython code to define the slice. All of you have used sliced objects. This is what slice is. It's simply a struct that has PyObject head, which gives the common base class kind of stuff, and three additional PyObjects, start, stop, and step. So even though this struct has more fields than the original PyObject, we can add additional stuff, and we can still use it as a PyObject when we need to. So I might have a pointer to this PySlice object. If I encounter an interface that needs a PyObject, I can just cast it to a PyObject and pass it around freely. Those callers don't know what they've got. They only know that they have a PyObject, and they're going to have to do some type checking to figure out what it is. So this gives us generic interfaces in C. This is the actual PyObject type check function that is called when CPython wants to evaluate if a type is of another, if an instance is of another type. And we can see that this is taking a PyObject star, a pointer to a PyObject, and it's calling PyIsType, and PyIsType is taking that PyObject pointer and it's reading the OB type field, which it knows every PyObject will have, and compares it to the type. So it's because we do so many of these type checks in CPython, we have macros to make them convenient. And here is a macro from the CPython library that checks if something is a slice. This is PySliceCheck, and it's going to call that same PyIsType function and give it a handle to the PySliceType, and we're going to use that to evaluate the type. And this is done throughout CPython code, at the C layer, we end up having to do things very similar to what we do in the Python runtime layer. We have to do type checking because all we're doing is passing around PyObjects. So this is the function, PyListScript is the function that when you give something to a list in the angled brackets, when you give something to get item, we need to determine, is that something like an integer or is it something like a slice? This is the actual code in CPython that does this. It first says, hey, you've given me this item as a PyObject, I don't know what it is it int-like? If it is, then we're going to convert it to a C integer, and then we're going to pass it on to another function. Then we're going to use that same macro we just observed, PySliceCheck, and we're going to see, is this a slice? We don't know, it's just a PyObject. If it is, then we're going to pass it on to another function. And then finally, it could be anything else, we're going to throw our arms up and say, hey, we don't know what this is, and we're going to prepare an exception. So when I think of CPython, when I think of what's going on under the hood of Python, we have a sea of anonymous kind of PyObject star structs floating around. Nearly everything in CPython is a PyObject star. Nearly all interfaces take PyObject star and then have to do type checking to figure out what kind of particular type we have. This gives us polymorphism, and this enables the dynamic behavior that is so important to Python. But doing this kind of subverts the benefits of using a statically typed language in the first place. The reason we wanted a statically typed language, well, in part, was to get strict interfaces. We don't have strict interfaces, we're just passing around PyObjects everywhere that we then need to figure out what they are. So, hopefully you understand now a little bit about how Python is working under the hood, and we can return to my initial paradox. But before that, I hope I've given you some perspective on where we are with Python now. In many ways, it's a language with two totally increasingly divergent layers. Static typing has functionality beyond the runtime. The runtime completely ignores these static components or leaves little traces of them. Runtime engagement is possible, but it is optional. And if you have these two layers, I strongly encourage you to align them. So what do I mean by that? Well, unevaluated typing is technical debt. If you are using type annotations at all, you should check them. I strongly, strongly encourage that. A problem is that your IDE is designed to handle gradual typing. It's designed to handle incomplete type annotations, but many of them are incorrect. And I've seen tons of code of just incorrect type annotations just sitting there, and it's a problem. So if you write type hints, you need to check them, and you need to do it up front from the very beginning. We have very many nice static analysis typing tools available these days, from MyPy, PyWrite, Ty, and we heard about Firefly earlier. Or you can actually do runtime validation. You can use those type annotations in the runtime to do the checks that you might be doing manually, which is kind of nice. TypeGuard is a tool for that. I've created a tool called callguard.check that does it for NumPy arrays and data frames, which is pretty cool. But back to our paradox. So what is a paradox? Well, there's a couple features. One is that a paradox often has an apparent contradiction while still being true. And generally, paradoxes have some sort of circularity. So let's return to where we started. Python implements dynamic type behavior using a statically typed language, C. We saw how that worked. Only to then offer static type annotations on top of a dynamically typed language. It's circular, it seems like a contradiction, but it's true. So, is there an alternative? Is this complexity necessary? You could say, why not just use a statically typed language? If you're using static types on Python, you should just use a statically typed language and forget all this complexity. But being flexible and gradual, which is a key feature of Python and a key feature of static typing in Python, is important, but it's expensive. It comes at a cost. But I think this is the way it should be, because Python succeeds and continues to succeed because it is not just one thing. It can be many things. If we're quickly prototyping, we can just be dynamic. If we're building libraries we're going to live on, we can statically type them, and we can align those types to our dynamic language and really have it both ways, which comes at tremendous cost and complexity. But I think it's worth it for the developer experience that we all enjoy today. That's all I have for you. Thank you.